Dr. Tom Dory has extensive experience in microelectronics, covering semiconductor fabrication, hybrid circuits, and package assembly and testing. He has worked in many different aspects of semiconductor manufacturing, including plasma deposition, RTP, and packaging technologies, while at the Intel Corporation. Tom was a member of the Arizona State University Chemical Engineering faculty as a lecturer teaching semiconductor processing and all transport phenomena. He is the author or co-author of over 20 patents and publications in the areas of semiconductor chemicals and package design. Tom works with ITM Consulting and is contracted as an R&D consultant for Fujifilm formulated products. Let's join Tom Dory as he discusses 3D package and assembly technology.
Welcome to this IMAPS PDC on the 3D package and assembly technology. We're going to cover introduction to different types of packages to get everybody on the same page, as it were. We'll then go into some 3D package options, including the more modern and fan-out wafer level package option. But also I want to discuss coreless substrates, get into some of the processing to make thin die for 3D packages especially, but all assembly. Some dicing methods, talk about how you're going to attach the die electrically to the package, both wire bond, flip chip, and regular. Also the flip chip package process, a little bit of detail there. When we're talking about flip chip, we have to talk about the solder bumps. And there's a wide variety of solder bumps that are used both in traditional 1-die or even 2D packages, but specifically in 3D packaging. We'll cover that. I want to talk about copper pillars, since that's a newer technology out. With any 3D packaging, the assembly companies have to get die from multiple suppliers. So there is some supply line management I want to talk about. It's how that's being developed, and maybe a little bit on standards, some thermal management, and a review of some of the cutting edge technologies, including the through silicon vias or TSVs, underfill process, and we'll end up with some more detail on the 3D assembly and summarize. All right, let's get going. So starting with, why do we have packages? Well, there's some obvious ones, of course. It establishes electrically connection of the integrated circuit chip, logic or memory, to the circuit board. Well, why do you need that? Well, the bump pitch on a flip chip process or wire bond pitch is too small to be effectively connected to a printed circuit board. That's much bigger circuitry, higher current, bigger pitches. Even in a fan-out wafer level packaging, there's a redistribution layer that takes that small pitch and fans it out to a wide enough pitch and copper metal that you can connect to the printed circuit board. So you've got an electrical connection, that's key. Protects the die from mechanical damage. All wafers today are thinned before they go into assembly. It used to be thinned down from 780 microns, 0.78 millimeters, of full thickness 300 millimeter wafer, to about 200 microns, 0.2 millimeters. Well, they're going down to 10 microns, sometimes 5 microns today. Now, keep in mind, a piece of paper, like in your notes, is about 25 microns thick. So this is thinner than a sheet of paper. Very easy to break. So the package protects it from mechanical damage, contaminants, so environmental contaminants, moisture, salt, sodium, halogens like chlorine, even potassium. All those will shorten the lifetime of the performance of the integrated circuit, so the package protects it. Thermal distribution, very important for stacked die packages. When you power up any semiconductor, whether memory or integrated circuit, it gives off quite a bit of heat. I mean, the junction temperature of a logic circuit is somewhere around 110 to 130 centigrade. Memory is a little bit lower. That's a lot of heat. If you're looking at watts per centimeter squared, it's huge. That has to be managed by the package to extend the lifetime, functional lifetime of the overall product. So that's thermal.